make a separate class inside our main one. That we just say whatever we name the searcher object.
Okay, so today we're going to continue the discussion on Q optimization. I'm hoping to cover most, if not all, of Q optimization so that we can start talking about transaction coming back next week. So I'm going to skip the discussion of several alternative plans. To give you a quick recap, this is one of the running examples we used. Towards the end of last lecture, we showed how you can go from all the way from about 500,000 IOs down all the way down to about only 4,000 IOs by simply reorganizing the sequence of the order of the way you do different operators. There are more alternative plans as demonstrated on this slide, which I will skip. I will ask you to review this yourself. But the point is, you can not only optimize the plan by reordering the sequence of how you execute those operators, you can also choose different algorithms for a particular operator. For example, so far for the join operator, even though we did change the plan by pushing down the selection operator, we also changed the plan by producing the intermediate results rather than doing those on the fly. Those help, but we stick with page-oriented network join for the join operator. What about using different join algorithm for that join operator? This essentially is what's going on this particular slide, which I'm going to skip, but you can carry out the calculation yourself, fairly straightforward, which shows you that not only reordering the operators helps, but trying out different algorithms for a given operator will also reduce query cost dramatically. So using this running example, the next thing we need to study is really how do we do this inside the database kernel. The naive solution, of course, is to do an enumeration-based approach. By that, what I really mean is enumerating all possible plans. Enumerating all possible plans. That, in a minute, I will show you, is impossible because the possible plan space is exponential. Exponential with respect to the number of joint operations you have, with respect to the number of joint operations you have. Okay? So enumerating all possible plans simply is not an option. The search space is too big. Okay? So you need to do some sort of searching that cut down the search space dramatically to something that's manageable. And what is needed for that? Well, we first need a closed set of operators. A closed set operator means that you take something in a model as input and you produce something that can be described in the same model. I believe I explained this at the very beginning of the semester when I talk about relational operator. For example, relational operator is closed, meaning that they take relational models as input and they produce the output that can also be described using relational model. The benefit of this is you can combine relational operators in arbitrary fashion because the output of one operator can be used as the input for the next operator. So this being closed property is really important for you to enable you to do that. For example. Okay? And the second thing we need is to be able to iterate through this plan space. Okay? What do I mean by quote-unquote plan space? Well, given an input query plan, the plan space for that input plan is really all other equivalent query plans. All other equivalent query plans. The key word here is equivalence. They have to be equivalent to be in the same plan space. Otherwise, it's meaningless, right? If you generate a super efficient plan but produce different outputs, then it's not considered to be in the same plan space, obviously. Okay? So that's what we mean by plan space. And you need to have an efficient method to do two things. One is to test whether two given plans are equivalent or not. Secondly, given one plan, how to quickly produce another plan that's equivalent to the input plan. You need to be able to do both in order to work through the plan space, trying out different plans. And lastly, you also need what we call a cost estimation algorithm. Right? Suppose given an input plan, you can produce another equivalent plan. You want to be able to estimate the cost of each of the two plans in order to make a decision which plan you want to go forward with. Right? So cost estimation is a critical component. And the important thing here to note is that cost estimation must be efficient. If you recall the example I gave you in last lecture, like driving from here to Boston, in order to estimate the cost associated with this route, you don't want to actually go driving that route and come back tell me the cost. Makes no sense. So you want to be able to quickly estimate the cost of a given plan without actually executing a query according to that. The final bit we need is, with all of this in place, we will need a search algorithm for the reasons I just mentioned, which is the plan space is too big. You cannot afford to test the cost or estimate the cost of each single plan and choose the most efficient one. That's just impossible because it's too expensive to do that. You have exponential number of equivalent plans in a given plan space. That being said, you need a search algorithm to quickly prune away a large amount of plans and focus or narrow down to just a small set of plans. And then for those small set of plans, you estimate their cost and you select the best among them. As I mentioned again in last lecture, this problem is NP hard, so which means there's no way to guarantee to find the optimal plan from your plan space. However, the algorithm we will be discussing will guide you through the plan space to find a good enough plan, and making sure that you don't end up with a really bad plan. That's essentially what will happen. Okay, and that's what most commercial database engines are using nowadays. Okay, so I'm gonna skip all of this because this basically recap what I said. So some highlights. So the optimizer I'm gonna introduce is known as System R optimizer. System R is a project started by IBM Research Ahmed Lab back in the 90s. Okay? Even though it's a very early day prototype, but it actually, if you look at the commercial database engine nowadays, most of them are still using the same framework as those designed under the System R optimizer. Okay. Of course, if you look at the optimizer, core optimizer inside a commercial database engine like Oracle, it's way more sophisticated than what we are talking about here today. However, the fundamental principle, the basic principle, is the same as what we will be discussing here. Okay. And one comment I want to make is about cost estimation. We will focus on, for the purpose of the following discussion, we will mostly focus on I/O operations, number of, in other words, number of page you're gonna access, read or write. Of course, in a real system, on top of that, you have CPU cost, right? The cost to execute a query is not simply just the cost of doing I/Os. Once you bring the necessary data to memory, you still have to pay CPU instruction cost as well as memory to cache data transfer cost, which is omitted in our analysis in order to execute a query. So you may wonder what happened to those costs in a real database engine for its query optimizer. Well, the point is most query optimizer will develop what we call a cost model to account for the memory to cache data transfer cost as well as CPU instruction cost. That cost model will derive what we call a coefficient for that cost, so that you can combine the I/O cost and those costs to the same unit. It's kind of like a conversion of different units. And under this unified cost model, then you can reason about cost estimation, okay, for your different query plans. That being said, for the purpose of this course, and in the interest of time, I will focus on just the I/O part of the cost estimation. Okay. And the next thing I want to talk about is the unit of optimization. If you think about a general SQL query, right? A generic SQL query can be really complicated. It can have multiple levels of nesting. If you recall what a nested query is, you can have multiple levels of nesting. And those are notoriously hard to be optimized, especially for those nested queries with correlations between inner and outer block. I hope you still remember what a correlation means for a nested query. If you don't, go back and review the discussion on SQL. Okay? Basically, very short, correlation means that the result of your inner block will change when you change the record you are looking at from the outer block. They are not independent. And those are really, really hard to optimize, as you can imagine, right? Because the cost of executing that inner block depends heavily on which particular record you are looking at from the outer block. In other words, it's possible that you might want to use different query plan for your inner block, depending on what is the current record you're looking at from the outer block. That makes it super hard. In other words, in another scenario, if you're looking at independent blocks, meaning the outer block and inner block are totally independent, the results of your inner block is a constant, regardless what record you're looking at from the outer block, then it's a much simpler case because there must be an optimal plan for that inner block, and it doesn't change even if you change which record you're looking at from the outer block. So for that very reason, nested queries are really, really hard to optimize, especially for those with correlations between inner and outer blocks. Okay? Does that make sense? So what people do in practice? There are some really sophisticated techniques you can cater for those nested queries with correlations. Again, for the interest of time, I won't go into detail of those. For the purpose of this course, we will simply assume the following simple strategy, which is to assume that inner and outer block are independent. Of course, this is not true, right? If you have a nested query with correlation, this assumption breaks down. But let's assume that's the case. Just as when people analyze random variables, in most cases, people assume that random variables are independent, which is not true, obviously. For example, to make prediction of Salt Lake City weather, you will assume that the weather in Salt Lake is independent from weather in Denver or Phoenix, but which is not true. Obviously, that's not true. But for the most part, it works okay. It works okay, even though there exists some level of correlation, but I ignore that. Okay, so that's what we will do. That being said, the unit of optimization for us is a single SQL block without any nesting, because we assume they are independent, so you can optimize them independently once you have that assumption. Is that clear? Okay. And we will consider only what we call left deep join tree. For now, just understand this. A left deep join tree is something like this, which means you arrange your join operators, if you have multiple of them, like a tree structure. And what's so special about this tree structure is that if you look at each level of the tree, if you look at the right branch of the tree, at every level, the right branch is always a base relation. A base relation means it's one of your original input relation in the from clause. So for example, at this level, my right branch is a base relation called B, A join B. Then at this level, my right branch is a base relation C. At this level, my right branch is a base relation D. Your left branch, except the first level, gonna be an intermediate result. For example, at this level, your left branch is an intermediate result of A join B. At this level, your left branch is an intermediate result of A join B join C. Except the first level, you have a base relation. Obviously, this is not the only possible join plans you can come up with, because join are, I forgot to bring any marker, so I'm going to use chalkboard. So obviously, this is not the only possible plan you can have. For example, it's totally okay, I can have something like this. Right? This is not a left deep tree though. This is not a left deep tree, because if you look at this level, the right branch is no longer a base relation. It violates the principle we just mentioned. Does that make sense? Yes? Now, let me ask this question though. Assuming that we limit ourselves to only left deep tree plans. We limit ourselves. If you look at the plan space, this is your plan space. And by this observation, you know the left deep tree plans this must be a subset of your entire plan space by this simple observation, right? You follow me? This plan space is huge, and we limit ourselves to only this space. It's kind of like this is the universe, and this is our solar system. But even this is already huge. Can someone tell me what's the size of this? Size of this subset of your plan space. Given n relations. Given n relations. Meaning you have n minus 1 joint operator. For one joint operator, you have two relations. Right? For n relation, you have n minus 1 joint operators. Like in this case, I have 3 joint operators, A joint B, joint C, joint D, with 4 joining relations. Given n relation, what's the size of this plan space, left deep tree plan space? Excellent. It's not exactly n factorial. It's actually larger than n factorial, but it's at least n factorial. Can you argue why?
Well, in place of A can be any of that. A, B, C, or D.
Yeah. So actually, if you just look at this plan, I'm gonna change that just a little bit. Instead of drawing like that, I'm gonna draw the same plan but like this. I put A, B, C, D in the same level. Topology-wise, it's the same tree. I'm just changing the appearance of the graph, but topology-wise, they're the same tree. Huh? Do you follow what I'm doing? Topology-wise, it's identical. It's just appearance looks different. I mean, it's just the same person, same Feifei, wearing different clothes. But it's Feifei, it doesn't change who I am. Does that make sense? But this is the one I just erased is a different person. It's not just wearing different clothes, it's a different person. But this is the same person as that, wearing different clothes. Now if I do this, what do you observe? You observe that A, B, C, D is at the same level. They are all at the leaf level. What can you, I think by now it should be clear where that n factorial comes from. You can take the same structure, but simply promoting this relation at the leaf level, you get n factorial already. By just doing that, you get n factorial different trees. By promoting those relations at the leaf level, you get n factorial plans already. But why there's more than n factorial plans? Can someone tell me now? Why there are more than n factorial plans? This gives you exactly n factorial plans, a permutation of those at the leaf level, right? Why the size of this is actually greater than n factorial, greater equal than n factorial? Well, first of all, I can use different joint algorithm for these strong operators. That already introduced more than n factorial plans. That itself. Does that make sense? Yes or no? Right? I can use page arbitrary natural drawn here, block natural drawn here, and hash drawn here, or I can use hash drawn here, and so on and so forth. I give you an exercise. Suppose I have 3 different drawn algorithms to choose from. How many plans that I will introduce on top of this n factorial? Now, it's not that simple, okay? I leave you guys to think about it. Then on top of that, you can also push down selection and projection operators. And different ways of pushing down those will introduce additional combinatorial choices you have. So you end up with, basically your search space is still huge. N factorial is not linear, at least. Does that make sense? It's exponential, essentially. So even if you limit yourself to here, it's still a daunting task. It's like we are searching whether certain elements exist in the universe, and searching through the entire universe is too expensive. We say, okay, let's limit ourselves to solar system. Much nicer problem to solve, but still a very hard problem. It's not that you're limiting to just your house. And depending on whose house it is, that can be, I mean, if I limit house to your house, to your apartment, probably that's easy. But if I limit to, say, Bill Gates' house, he probably has a big house. I actually been to his house. It is big, I can tell you that, I can verify that. So it's still gonna be a daunting task. Alright, so I'm gonna use the same examples. So that's the premise of our discussion. I hope by now you follow what I'm saying. We're gonna limit ourselves to this space and ignore all the other guys because we just simply cannot afford to search through all the plans. We're gonna limit ourselves to this, but even this is huge. Even this is huge. So the first step is to represent your query in something that the underlying engine can understand. This actually is fairly straightforward. You translate your SQL using relational algebra. We don't have a project for this. For your project 3, I give you a parser library. You just link to your code. But this is not that hard. If you have ever taken a compiler class, and you know something like things like, yeah, you know what I'm talking about, right? This relational algebra operator becomes symbols in your Yacc compiler, and you translate your the operator in your language. In our case, it's SQL, but in Yacc you can do this for C or C++ or Java. Those symbols, those operations in your language translate into corresponding symbols. Blah blah blah. You do those compiler tricks. Okay? I'm not going to go into detail. This is not a compiler class. If you're interested, take a compiler class. You know how to do this. Okay? Taking a SQL and translate that into relational algebra representation. Think about relational algebra operators as symbols in your assembly language. That's how this compilation is done. So this part is not that hard. A very standard parsing and compiling trick. We'll do this. Okay. So this we'll do, and then this may be translated into, a relational algebra representation with certain levels of nesting. But that's okay. As we said, we're going to assume independence between blocks, and we're going to optimize each block independently one by one. That reduces our problem to just one block at a time. So we will focus just on a single block. A single block means what? The most complex form you can get out of a single block is what? Select from, where, go by, and heading. That's as complex as you can get. You cannot be more complicated than that because, as I said, multiple times by now, we limit ourselves to a single block each time. Make sense? But the tricky part is in the from clause, you're going to have potentially multiple join operators, not necessarily just one join operator. Right? So that takes care of objective number 1, which is we now have a closed set of operators, and we have an initial input plan. Whatever the output from your compiler, from SQL to relational algebra representation, so we take our objective number 1. We take our objective number 1. Now we move on to objective number 2, which is to test whether two given plans are equivalent, and also given one plan, how to enumerate other equivalent plans. So now we're moving down to objective number 2. So for objective number 2, this is officially known as relational algebra equivalence. We're no longer in the SQL space. We are in the relational algebra space. Okay? Now our task is reduced to test whether two given queries represented by relational algebra operators are equivalent or not. That's essentially what we need to do. For this, our approach is to look at each operator case by case. If we understand the equivalence of each operator, we understand the equivalence of the combination of them. Okay? So, for selection operator, the equivalence, you have essentially two equivalents. One is if you have multiple selection conditions, note that I'm using only AND operation here. Why is that? Can someone argue? You may argue, wait a minute. In the general case, for a selection, I may have AND or not. Why you focus only on AND? Can someone tell me that? We talked about this before, actually. Why? As I said before, any logical expression can be break this CNF down to just one term at a time. I can have multiple selection operators. Each operator is associated with one term at a time. They are equivalent. How do you prove this? You can prove this using a induction approach, meaning that if having n selection condition is equivalent to having n minus 1 selection condition with one more selection in the outer block, then you can do an induction to prove this for the general case. I'm not going to go into detail, but that's kind of the way to prove this. The second equivalence for selection operator is that you can commute. In other words, change the order of your selection terms without affecting the output. Right? If you do selection condition 1, then selection condition 2, then selection condition 1. It is equivalent to just do selection condition 1, for instance, selection condition 2. Okay? So fairly straightforward. For projection, it's a little bit trickier than selection. Suppose you are projecting out A1. By the way, A1 here is a symbol. It doesn't necessarily represent a single attribute. It can represent a set of attributes you are projecting out. It's just a symbol. Okay? Not necessarily just a single attribute. The equivalence is that in order to project out A1, it is actually equivalent to project out any other attribute of your choice and project out A1 at the end as long as you include A1 every step along the way in your projection list. Meaning that project out name from student is equivalent to project out name from projection of name and GPA of student. As long as you have the final projection attribute or attributes in the projection list every step along the way. Does that make sense? Okay. So that's the equivalence for projection. Now for joins satisfy both associative and commutative properties, meaning so I don't know why it displays as cross product. It should be join operator. I will fix this in the slide. It should be the join operator instead of course, cross product is a special case of join operator. So cross product, if join operator satisfies these two properties, cross product obviously still satisfies these two properties. So this is what we call associative and commutative property. And for this reason, you have that n factorial size for elective treatment. It is because of this. Okay. And there are more equivalents, which is a projection commutes with a selection that only use attributes returned by the projection. Do you follow this argument? Meaning, if you do a projection, then selection, some condition C, and this is the equivalent to if and only if the term C uses only A. Right? Uses only the attribute. Of course, this A may not be a single attribute, it could be a set of attributes. I think this is very clear, right? Because if condition C uses some other attribute, you cannot commute them. Because if you do, you can no longer perform this selection condition. Because those attributes that C will be using is projected away. Right? You can no longer check those conditions. Okay. Selection between attributes of two arguments of a cross product converts cross product to a join. This is basically saying that selection condition C of R cross S is the same as R join S with condition C. Right? This essentially is this equivalence. And a selection on just attributes of R commutes with R join S. Meaning if you have a selection over R join S, and that selection touches only attribute from R, you can do selection first and join. We saw this actually. Pushing down selection over join operator is exactly this. That's exactly what we did. Similarly, if a projection follows the join operator, we can push down the projection operator, but here you have to be a little bit careful. You can only push down that projection operator if and only if not only you keep the projection attribute, you also keep the join attribute. So you keep both the join attribute and the projection operator, projection attributes when you push down a projection operator, okay, over a join operator. I think we're done with object number 2. We know at this point you're dealing with a single block represented by a set of relational algebra operators, and we know all the possible equivalents among them, so we can not only test whether two are equivalent or not, we can use how you generate another equivalent plan. Why don't you just use one or multiple of these equivalents and morph your plan based on this? You get another plan. So we know how to test whether two are equivalent. We also know how to generate an equivalent plan given an input plan using one or multiple of these equivalences. So far so good? So we're done with 2 objectives already. Let's moving on to the third target, third bullet in our list, which is cost estimation. We need to estimate the cost of a plan so that we can choose among 2 or multiple equivalent plans which has smaller cost. That's our objective number 3. And this is where we're going to talk about that long overdue promise I made, which is the selective estimation, how to do that. So we must estimate, if you think about it, the cost estimation boils down to, you can do this recursively. In other words, our plan is represented by a tree structure. In particular, it's represented by a lefty tree plan, like this. Because we're limiting ourselves to this subset. So any plan will be looks like this. They differ only in 2 things. One is what the leaf level look like, how the ordering of the relations are in the leaf level, and also what algorithm you are using for each join operator, and whether you push down selection or projection. They only differ by those. You follow me? In terms of the tree topology, they are the same. It's always a lefty tree. That means that to estimate the cost of this, it boils down to what? You can do this in a bottom-up fashion. You estimate the cost of this, and then you estimate the cost of this. Finally, you estimate the cost of that. You do this bottom-up. Does that make sense? Yes or no? We start with the base case, which is this. This must be easy, because this is simply a joint cost estimation, which we already know how to do. Knowing the joint algorithm here, whether it's a block nested or page oriented, whatever, we know how to estimate the cost. I spent almost an entire lecture on that. How to estimate the cost of this. If there is an if though, if you know the size of A and B. By size, I mean those typical statistical information on A and B, such as number of pages, how many tuples in each page, so on and so forth. But those information are typically available, as I demonstrated a long time ago, in what? In system catalog. Remember that system catalog discussion I actually demonstrated using the PostgreSQL server we have. Right? I show you where those information are stored at, and in your implementation, you should notice they are stored just at another table in your database. So I know how this is taken care of. You know what I mean? Now, moving down to the next level, it shouldn't take you a long time to realize this is exactly the same problem. If I view this, if I replace A join B using a temporary relation T, isn't this the same? Join over two tables. So I can do the same trick. But wait a minute, there's something missing though. What is missing? In order for you to estimate the cost of this. Suppose you know what join algorithm you're using here. What's missing? What's different from estimating the cost of T join C versus the one we just did, A join B? You all know how to estimate the cost of A join B, right? You all should know how to do this by now. If you don't, you should go back and review that query evaluation lecture I just had. So what's the difference between estimating this and estimating the cost of this? What is a fundamental challenge that we haven't overcome yet?
You know the size of T.
We need to know the size of T. We need to know that. Why we don't have to worry about this case? Because these are base relation. They are given. The statistical information of A and B are given to you by the system catalog. But the underlying system is, there's no way for the underlying system to pre-compute statistical information about T for you. Because if you try to do that, it's impossible. Because just to join A and B, there are numerous number of possible join conditions. How can I possibly pre-compute all such possible scenarios and pre-store the statistical information for these different T's in my system? No way. There's no way I can do that. So you have to do this on the fly. That make sense? But this boils down to what? This boils down to the bullet point over there, which is estimate the size of the result, which is essentially, again, the long overdue promise, which is size estimation. Selectivity estimation. Okay? Selectivity estimation, so we backtrack our problem. Now, before I move forward, suppose there's a black box that can do this for you. Selectivity estimation. Then we know how to estimate the cost of this. Then the whole problem is solved, right? Because then I replace this with T prime. I use that selective estimation box again. I can estimate the statistical information of this. This reduced to this, then I can estimate the cost of that. I'm done. That makes sense? So I reduce my problem to the core problem of all, which is just estimating the size of the join. So I reduce this complex problem all the way down to this one problem. If I solve that, the entire puzzle is kind of like they all depend on each other. If you solve this, everything collapses. It's like one of those games you play, right? Like you stack multiple, I don't know, little square blocks together. You animate, take turns, take out a block, and finally go to that one block that if you remove, the whole tower will collapse. Right? We've identified that one block, which is that selective estimation. Now, but before we talk about selective estimation for the join operator, we start with something simple, which is selective estimation for unary operator. Join is a binary operator involving two tables. Before we tackle this problem, let's tackle the problem of estimating the size of unary operator, which is selection and production. How do we do that? Does that make sense? Okay. So, that's what we're going to do next. So remember, our objective is to estimate But before we tackle this, we will reduce this problem to unit operator, which is selection of R, of some terms. Why this is relevant? Because this typically is reduced to this. And oftentimes I can even push down the selection operator inside. So in order to solve this problem, obviously you need to solve this problem first. So selectivity estimation of this. How do we do this? In other words, what's the size of this? What's the size of this? Knowing, of course. Set of R and some other statistical values such as number of tuples, number of pages, distinct key values, low and high key values, and index height, and number of index pages. Those are some basic statistical information about your table that database will store in the system catalog. And catalog, of course, these values, if you think about it, it's a dynamic database that receives updates over time. The values of this statistical information will change over time. You can either maintain these statistical values in real time whenever you have an update, which can be potentially expensive. I will explain in a minute why that's expensive. Or you can do this periodically. For example, what's the number of students in University of Utah? If I did a tally at the beginning of November 1st, we have 3,256 students in Utah, for example, University of Utah. 3,500. Of course, it's a made-up number, right? We have way more students than that. But let's say on November 1, we have 3,526 students. Now, on November 5th, I ask you how many number of students you have in University of Utah. What do you do? Well, either you go back and you count again and come back and tell me, or you just use that estimation from November 1st, and knowing that the admission typically happen in beginning of fall and beginning of spring, it should be a very reliable indicator, maybe off by 1 or 2, right? But cannot differ too much from the truth. So that's what we do. And the challenge of this, though, is that this C, condition C, is a conjunctive normal form of multiple terms. It's not just a single term. In the general case, it's something like this. In the general case, it's something like this. All right? Like what I have here. So the selectivity, or what we call reduction factor, if, again, this is a big if we assume that these terms are independent from each other, and suppose each one of them has a selectivity, what we call reduction factor. Like, what I mean is, if you just do this, so that's the reduction factor of T1. So that's the reduction factor of T1. I define this for each T, of course. Each term. You follow me? Yes or no? Yes? Or no? Okay? So that's how I define reduction factor for a given term. Now, if I have the reduction factor for each term, for this conjunctive normal form, what's the reduction factor of this general condition C? Well, in the general case, you don't know. Why? Why you don't know? Because different terms may have correlations. I'll give you an example, right? Select student from South Utah. South Utah defined as whatever to the source of St. George. Okay? And there must be a reduction factor of that. And selection of student from Idaho. There's a reduction factor of that. These two are obviously independent. you cannot be both from Southern Utah and Idaho. Impossible. So suppose the first reduction factor is 10%, meaning on University of Utah campus, 10% of students are from Southern Utah to the source of St. George. You follow me? 10%. And suppose the reduction factor for the second career is 1%, meaning the 1% of students in University of Utah are from Idaho. What's the overall reduction factor? Meaning selection of students from. Actually, this is a bad example because that's 0. That's 0, right? Let me give you another example. Let me change the second career to. The first one is selection of students Southern Utah. The second one is selection of students from Utah. Now they overlap. At least they overlap. And let's say the first one is selection of Southern Utah students. This is, let's say, roughly 10%. Selection of Utah students. Assume that in University of Utah, let's say 70% are from Utah. Now, what's the, the reduction factor? What's the reduction factor of selection of U and Southern Utah? Someone make a guess? Do this. This should be fairly easy, right? In this case, it must be just 10%. Because whoever from Southern Utah is still part of Utah, right? So once you do this, the reduction factor of this is 1%, 100%. It doesn't reduce at all. It doesn't reduce the size of your query at all. Does that make sense? But what if I change this to age greater or equal to 20? Now suppose I have 70% of students older than 20. Now what about this? What about this query now? What's the reduction factor here? It's definitely no longer 10%. What is this? Well, in the general case, you don't know. Maybe if I give you this assumption that, it's, again, no offense and no discrimination. Assuming people from Southern Utah, quote unquote, are old. They're all above 20 years old. Right? Then what this will be? This will be 70%. Because the selection condition of Southern Utah with regard to 20 older than 20 has no effect, has no reduction at all. Do you follow my argument? Yes or no? If everyone from Southern Utah are above 20 years old, then that first condition has no effect. But in general case, we know that's not the case. Assuming the age distribution and the geographical location distribution of students are independent, they're independent. Assuming that's the case, what's the reduction factor here? In other words, the general student, if you look at the general student population, there are 70% of them above 20 years old. If we assume that age distribution is independent from where they are from, what that means is if I just look at Southern Utah, there should be about 70% students above 20 years old as well, just as if you look at the general student population. If I tell you that, what's the reduction factor here? Can someone tell me? Huh? 7%. 7%. This example shows you what I'm going to argue next, which is if you assume that these terms are independent from each other, which we know may not be the case, right? For example, what if the age distribution do change if you look at the geographic location? For example, I assume the age distribution in Florida must be skewed to older people because people retire there. If you don't trust me, go to a gas station in Florida and go to a gas station in Give me a place with young people. Gas station in California, Bay Area. Bay Area has a lot of you guys, right? It must be young. I mean, the age distribution obviously is different. However, assuming in the general population that's the case, then they're independent. You can multiply, the argument is exactly this, which is, if the terms are independent and you are using a conjunctive normal form, the overall reduction factor is simply the multiplication of reduction factor for each term. Later on, I will show you how to cater for the case when this is no longer the case. Right? What if the age distribution is correlated with the geographical location? If they are not independent, what do? You cannot simply multiply them together. Like I said, if all students in southern Utah are above 20 years old, this magically becomes 70%. 10-fold difference. It can be a huge difference. That make sense? But for now, we're going to assume independence between terms in a conjunctive normal form. The reason I'm doing this, again, is to further reduce the problem we try to solve. Because if you try to estimate, do selective estimation for a general conjunctive normal form term, that's hard, because I have multiple terms, difficult. Now, I'm going to assume independence among them. If I do that, my problem is reduced to what? Selectivity estimation of this, reduction factor of this, is reduced to just estimating reduction factor of one term. Because if I can estimate one term, I just do this for multiple terms and multiply them together. So I reduce my problem even further down. So I'm reducing my problem to just, from here, I reduce to just a single term over R, and I want to estimate the size of this. Of equivalent, I want to estimate the ratio of this. Estimating the size of this is the same as estimating the ratio between the two, because you know this, you know the size of this. So I reduce all the way down from here to here, then to here. That's what I'm doing. Right? Now we're down to a single term. Single term. I want to estimate the selectivity of that. In other words, it's a one-dimensional range query. If you have multiple terms, it becomes a multi-dimensional space. Right? Like I can draw my students out. This is geolocation. This is the age, and a student is simply a point here. Southern Utah, 25 years old. Southern Utah, 26, 27 years old. Southern Utah, 18 years old. Idaho, 25 years old. So each student is reduced to a point. And if I have a conjunctive normal form, I'm essentially doing a multi-dimensional query. I'm looking at cutting some lines over this multi-dimensional space, which is hard. So what I did is assuming independence of the two, so that I reduce to just what? I have only one dimension. I don't have two dimensions anymore. I only have one dimension. So points are distributed along this one dimension. But they can stack up. Stacking up means that this point takes the same value with respect to this dimension. So that's essentially what I have. We reduce our problem to this. Okay? Yes? Now, for a single term, there are only a few possible scenarios we need to look at. One is, now what are the possible forms for that single term? The first possible, the simplest form is what? You have a selection condition. The term is column equal to value, meaning an attribute equal to some constant, like age equal to 20, geolocation equal to southern Utah, or state equal to Idaho. State is your column, value is Idaho, for example. Column is age, value equal to 20, that's another example. So how do you estimate this? If you don't have any other information at all, if you rely only on the system catalog, there's nothing much you can do. How am I supposed to know how many students are from Idaho? How am I supposed to know how many students are age of 20? From the University of Utah, I honestly don't know. Unless you allow me to look at each student and ask each of you, where are you from? What age you are? I will conduct this, meaning that you have to do a linear scan of, or do a query of your entire database to figure this out. And suppose you don't have that, what do you do? Well, database use a simple naive approach. If you don't have any information whatsoever, what do? You assume uniform distribution. If you assume uniform distribution, the selectivity of this becomes 1 over what? The number of distinct keys you have on that column. Right? Obviously, this is not true, right? In our example, let's go back to selection state equal to Idaho, and how many students are from the state of Idaho. What you're telling me is we have equal number of students from Idaho versus equal number of students from, let's say, Utah. In the University of Utah campus, this is obviously not true. We have way more students from Utah than from any other state. That make sense? But if we do assume uniform distribution, meaning that number of students from Utah is the same as number of students from Idaho, number of students from New York, number of students from California, then a selection on one particular state, the selectivity of that must be what? 1 over 50. Right? We have 50 states. Okay, that's essentially the first one says. Now, if you understand that, what about this one? Column greater than value. That's a range word, right? In other words, how many students age larger than 20 or older than 20? If, again, you assume uniform distribution of age values, and you know the lowest key and highest value on that dimension, on the age dimension, the selectivity becomes what? The selectivity simply becomes the width of your entire range of your domain divided by the width of the range you are selecting. Simply this one. What if you have two values, greater than or value 1, less than value 2? Well, then you change the high value with that value 2, minus 1 value. Again, this only works if what? If you assume uniform distribution. What if you don't? I will talk about that next. But before we do that, let's think about yet another term. The other possible form for a single term is column 1 equal to column 2. This actually connects what we are discussing now with the join discussion. Because join is essentially what? Join is essentially a join is essentially something like this. You do the cross product so that this actually reduces to just a single table T. Right? And you can estimate the set of this very easily, which is simply the set of R multiply set of B multiply set of B. So you know the set of T very easily. So the join selective estimation reduced to this term over a single relation. That's the connection. That's why I said column 1 equal to column 2 become handy for join estimation, because you can convert a join to a cross product of the two, and you know the cross product size by almost for free. You simply multiply the size of two relations, you get the size of the cross product. So it reduces this join back to a single table. So it reduces to this problem. How do you estimate this? Right? You follow me? Now, if we assume uniform distribution on both column 1 and column 2, can someone argue for me what's the reduction factor there?
If you've got, so you were saying the same number of keys for column 1 and column 2, right?
Not the same number of keys for column 1 and column 2. They may have different number of keys for column 1 and column 2. but we are assuming uniform distribution of both columns.
Oh, okay, well in that case, whichever one of the columns has the greater number of keys.
Why is that? That's the right answer, but why is that?
Because when you're doing the join, it would be, how do words? Whichever one has the greater number of keys is going to be the determining factor when you're combining the two.
It is the determining factor, but we need to understand why that's the determining factor. Like you can argue, the U.S. has the most powerful military force on Earth. Why? Why that? You cannot tell me, oh, because U.S. has the most powerful military on Earth. But sometimes I get into an argument with people like that. Like why Alabama is the best football team. You know, for this, I actually buy that because it is the best football team, period. Don't argue for it. I mean, it's like, okay. So, why is this? Okay, this actually is not that trivial to make this argument. Assuming uniform distribution, the point is, this is equivalent to what? This query is equivalent to selection of A dot C1 equal to, suppose I'm going to make some assumption. I'm going to assume that for R, okay, R cross S, R and S, two separate tables. R must have a column, R may have multiple columns. There must be a column called, so this is changed to be consistent with my notation here. Table R has a column C1, and table S must have somewhere a column C2. Right? I may have additional columns, but these are the two columns I care about. You follow me? And each column might have different values. We may have duplicates because these are not necessarily the key for R or S. You follow me? That's kind of the setup. And I'm going to assume that the distinct keys, distinct values for C is distinct value for column 2. Do you want my argument? Is from B1 to B2 to Bn. Distinct values, meaning that this could be, for example, B2, B2, B1, Bn, Bi, so on and so forth. You may have duplicates, but distinct wise, I'm going to have m distinct values here. Similarly here, for C1, I'm going to assume they are A1 to A2 until A small n. Follow me? So this could be A1, A3, A4, then A2, A2, somewhere in the AN. That's what it looks like. By enforcing a joint condition, you also know the fact that any AI and Bj must form the same universe U. They must form the same domain. They must be all integer. Or you cannot say, oh, 5 equal to elephant. 1 is from the universal integer, 1 from universal animal. That makes no sense. Right? That's obvious, right? In order for you to enforce a joint condition, it must be comparable, right? Do you follow what I'm saying so far? So the question is, how do you estimate the selectivity of this? Assuming uniform, by the way, uniform distribution means what? Uniform distribution means, so this means number of AI always equals to number of AJ for any I and J. Here, number of BI must equal to number of BJ, even for I not equal to J, for any I and J. That's what uniform distribution means. Of course, in general, this of course is not the case, but assuming that's the case, right? Do you follow me? In our case, this M and N, this is N, this is M. Number of distinct keys for the second column, number of distinct keys for the first column. This is N, This is an M in my notation here. So far so good? You follow the discussion along? So far so good? No question, okay? Now we need to show that y is 1 over the max of the two. So basically the argument is the selectivity of this divided by, of course, divided by the size of R cross S is 1 over the max of N or N. That's essentially the claim. Right? Meaning that this over this is this. We're arguing that this is this. Now with all that said, now can someone help me figure this out? Why that's the case? I can leave this as a final test problem, okay? First of all, you all know at least the setup and what we are trying to prove, right, by now. If it was not clear 2-3 minutes ago, but now I hope at least that's clear. What's the setup and what we're trying to prove? Do you follow? I mean, in the general case, it's even harder. If you don't have uniform distribution, this is way harder, of course. So a hint I'm going to give you is that you can rewrite this grid in 2 different forms. In the first form, this is the equivalent to selection of R dot C1 equal to B1 over S union with selection R dot C1 equal to B2 over S all the way union to selection of R dot C1 equal to Bm of S. I simply enforce all these the joint attribute from R, which is C1, to be equal to one of the possible values C2 may take. I union that. Of course, I have to be careful here, which is I have to do this for let me use C1 in general. But I cannot do this for just column 1. I have to do this for what? Each possible value of C1. That make sense? Yes or no? Right? For each value of C1, I check what values from those m distinct values will equal to that. But essentially, that's like saying this. Alternatively, actually, I think I made a mistake here, which is you should do the selection over R, not instead of S. Right? You are taking, if you think about what we're doing, is we're taking each value of B1 that actually exists from what? From S. And we probe into R, see whether how many records of R equal to the value of B1, how many records of R equal to the value of B2, and how many records of R equal to the value of Bm. You follow me? That's essentially how many will satisfy the condition here. Yes? Symmetrically, you can also rewrite this query to what? Now can someone help me with the second rewriting? Huh? If you do this for R, you can do this for S as well. C2 equal to what? Yes. Right? I can also rewrite this query to this. Now, this rewriting this become, each of this become a form of what? Column equal to value. we already argued if it's uniform distribution, the selectivity of this is what? It's simply 1 over m for each of these terms. And they're all together, so the overall selectivity is simply this. Here, the overall selectivity using the same argument is 1 over n. So the overall selectivity must be either 1 over m or 1 over m. It can only be one of the two. But y is the smaller of the two. Y is the smaller of the two, not the bigger of the two. Do you follow my argument so far? The selectivity of each of these terms is simply 1 over m. The selectivity of this term is just 1 over n. So the overall selectivity, because I can rewrite it like this, so it must be 1 of the two. Right? It must be 1 of the two. You follow the argument? But y is the max of the two means a smaller of 1 over of the two, right? So y is that. Say again? Can you speak louder? We throw away the extra. Yes. But why? Why? You need to formulate the argument. So I will leave this as a brain teaser problem for you to think about. Right? Coming back on Tuesday, I will explain it. But I mean, we are almost there. Okay? But I'm not going to let you go. I'm going to continue. Okay? But there's a small kind of puzzle I leave you as a homework exercise to think about. But at least you understand the reduction and y is either 1 over m or 1 over n. Right? At least you understand that. Because we essentially reduce this to column equal to value, which we already understood how to do, assuming uniform distribution. What if we don't have uniform distribution? What if we don't? If we don't have uniform distribution, the problem becomes much, much harder. If we don't have uniform distribution, what it looks like. Note that we're dealing with one dimension, right? So assuming my domain can be sorted from small to large, I impose some sort of ordering of my domain. For h value, that's easy, right? H is naturally ordered. But for state, it's not necessarily ordered. What do you mean by ordering state? You can order them alphabetically or some other state, some other way of ordering them. But suppose you come up with a way to order your domain. Then you say this is the value of A1, this is the value of A2, value of A3, all the way to, let's say, value of AN. Possible value you may take. Okay? What is this? This is the frequency. In other words, number of records having a value AI. Okay? The frequency. For uniform distribution, what this picture should look like. They all share the same frequency. They all appear the same number of times. Right? That's a uniform distribution. You follow me? If it's, but in real life, in real data set, this obviously is not the case. In real data set, what this picture looks like. What this will look like? Well, I don't know. I mean, it might look like something like this. It could be a really, varying distribution over different values. Right? Yes? For uniform distribution, I actually don't have to remember this many values. I can ignore each of these curves. I only need to remember this value n and total number of records. And I simply use total number of records divided by n, I get exactly the height of this curve for each value. So I only need to remember a single value of n and the total number of records in order to divide how many records having a particular value. But you can no longer do that for this. For non-uniform distribution. So how do you do this for non-uniform distribution? That's why the selectivity of column equal to value for this, the reduction factor of this, assuming uniform distribution is 1/n for this gradient, right? But that's obviously no longer the case if you come to this side of the picture. How do you estimate column equal to value? Well, the only way to do that exactly is what? Knowing each frequency value exactly. There's no other way. But that's too expensive, right? If I have n records and each record has multiple columns, you are telling me to remember this for every single column for every distinct value. That's super expensive in a database. So people don't do this. What people do is do some sort of approximation. I run out of time. I will continue this discussion on Tuesday. And think about the challenge, little challenge I asked you to think about. Okay, coming back on Tuesday, we will talk about that.